that. I sometimes feel like I should just put 30 minutes worth of SEM shots and we can just go through and just start looking at metal powder. But I won't bore you with that today. I'm going to try to get up here and tell you a little bit about metal recycling and try to convince you to look a little bit deeper at your scrap. And see if you can unlock the value of it. So MolyWorks Materials, it was founded in a shipping container on the front lawn of my CTO's house. We started there because we didn't have very much money and we needed to build a metal atomization system and we didn't want to get wet. So from that point on, the company has significantly matured and we've started to move into what I'd like to call kind of a growth stage of a startup. So we have over 7 contracts with the US government, and they all revolve around innovation and research grants, totaling over $3 million, or right around $3 million worth of contracts. We also have institutional venture capital and strategic venture capital. One of the largest oil field service providers in the world is a strategic investor and a trusted partner in basically the development and the rollout of what we're trying to do. And we also have had angel investors, which were really core to our ability to get to the point where we are today. We had a USPTO, a prolific patenter, as a very early angel investor. I mean, he had 77 patent applications in 10 years. Definitely deserved for that award. Former Secretary of the Army, that is the highest civilian rank in the Army. It managed over 1 million employees and a $90 billion budget. And then we also have the Vice President of Intel as an angel investor. And finally, we wouldn't be a Silicon Valley company if we weren't trying to implement tech. And we are also a technology grant awardee of Amazon AWS. And we are trying to apply the Snowball, which is an edge compute device, to our process. Basically using our vertically integrated manufacturing process and getting it onto the cloud so we can apply sophisticated tools like machine learning and artificial intelligence to enhance our process. So I don't really show this slide to discourage us from mining, but what I want to show here, or what I advocate for, is we need to be really conscious of the resources that we have. And that is not that we're going to stop mining, but we should look at what we've already mined and consider that as a valuable resource that we should start extracting a lot from. And if we don't, we're going to indebt our future generations to a point where they're not going to be able to do anything about the problem. So this is, I guess, maybe a fundamental thing that we've been talking about and people have been discussing here today. But what I'm going to try to show is our method to try to impact this major problem. So traditional manufacturing generates a lot of scrap. Over 60 million kilograms of titanium scrap will be generated just this year. So what if we could do something with that scrap that improved the adoption of additive manufacturing, that furthered us on the traditional, or that furthered us on the technology curve and started reducing our impact? So first place you look is you go for famous scientists. This is Newton. He had this idea of turning base metals into gold. And that's a pretty good idea. I'm a chemical engineer, so that sounded like maybe a problem I could start solving. Started looking into Newton's experience in it, and he really made no success on it. 0 base metals turned into gold, and then I thought that's probably not a route that we should really start pursuing. One of the most famous scientists in the world spends, I guess, a lot of it, later half of his life trying to develop this and had no success. One thing that I did like was his name, Green Lion. That's actually a pretty cool recycling name. Especially in the Lion City that we are today. So we decided that maybe we should look further back. And Cleopatra, the alchemist, had this great idea that was simple. I could understand it, so it seemed like something we should really consider. It's Ouroboros, and it means where the beginning is the end and the end is the beginning. And it's basically that whatever you produce, you also consume to make the next thing. And so that was something that we could kind of latch onto. something that we thought we could start to extract and something that we could use. And so this is our solution. We take metal scrap and we convert it into additive manufacturing grade powder. And we do that in the system that we built on the front lawn of my CTO's house. And then we can also take that powder and 3D print it into a part. So there what you're looking at is titanium metal scrap from a major airframe manufacturer, metal powder, titanium that we produced, and then a 3D printed part that's for a small adaptive jet engine. And this really starts to become powerful when you think about what this could actually mean. And if we start looking at all the metal that's out there as something that you can bring in and maintain and keep in your economy, then you can conceive an economy where every time I melt metal, every time that I add value to it, it remains in my economy. And so every year, my value or the value of my company actually starts to increase. And it increases basically exponentially. And it also opens the door for new business models, maybe recycling as a service or something that's a little bit more wild, like leasing metal. So this is fundamentally the vision that we have, and we're trying to execute to it. Initially, we're going to basically sell metal powders in a traditional route, not to disrupt the industry too fast, so we can actually make traction. But in the future, we do believe that there will be opportunities for us to have a more progressive, a more advanced, and a disruptive model. A way to allow the consumer or the user to get into using titaniums or more prestigious or higher value metals at a lower cost. But with the idea that at the end of that use, it's going to get recycled. And this is what that model or that economy looks like to us and what we've executed on. So the first one is, again, the scrap. Then you go directly to metal powder. Then you print the part, and each of our parts have a QR code or basically a manufacturing code on it. That was done to get rid of travelers. I don't know if any of you have travelers, but metal powder in a facility with travelers, and if the travelers are paper, is a nightmare. You're going to get powder everywhere. Powder's going to start coming into the office. It was kind of a horrible idea. And so instead we have everything in a digital sense, and that's all linked to the manufacturing code. And we've also a little bit inspired by the concept of what Amazon's doing with QR codes and logistics. And so the concept or the thought that we'd like to actually get to is each one of the parts that we've printed or one of our partners has printed has a QR code on it that when the part gets to the end of the life, it is then sent to the nearest MolyWorks recycling center for reprocessing. Titanium is especially useful in this because even in the state of Washington, a titanium part can be sitting outside in the pouring rain for years and not build up any rust. And we can take that material and then bring it in and recycle it. So I think there's actually advantages to thinking of for that.
The Global Manufacturing Industrialization Summit Connect Asia Pacific is happening in Hall 2 Workshop 8. Kindly proceed there now. Thank you.
There's an advantage in actually thinking harder or thinking longer about the materials that you use. Why recycle? I think everyone in this room kind of understands the need for recycling, but I think people maybe don't appreciate the economic value for it. So this is a study that's done by the Environmental Protection Agency of the United States. The numbers are, I mean, they're pretty obvious. We have energy savings, we have raw material savings, mining waste savings, air pollution, water pollution. The numbers really speak for themselves. And one of the major reasons why things are not recycled more is the fourth segment of the circular economy, which is the collection and the logistics or the sorting. And that's part of what we're trying to do with the QR codes and the distributed aspect. So if you have recycling centers that are closer to where the scrap is, you're going to get higher recycling rates and you're going to improve our utilization of Earth's natural capital. And this, I think, is something that we need to do, otherwise there's going to really be no future here. So the metal market is rather large and additive plays an extremely small part of it. Right now, our big focus area is titanium, which may seem small. It's only 3% of the total metal market, but it's 30% of the additive market. And we're specifically, or I guess we have an advantage in this space for cost, quality, and this is our biggest opportunity right now. MolyWorks has produced all the other alloy families: steel, stainless, aluminum, copper, niobium, silver, aluminum. We've produced many different alloys, but the focus right now is on titanium. The market right now, the thing that's stagnating the demand for additive manufacturing, or really the adoption, is two main things. It's material cost and material selection. What I think is really interesting is how fast material selection has grown over 2 years. So 2 years ago in 2015 or 2017, there was material selection wasn't that big of a deal to the users. I think people were just really trying to get their feet wet on additive manufacturing and understanding how they could implement it and deploy it. But now, once people have experience with the alloys that are available, they want their alloys. And they can get their alloys if we recycle their scrap. And if our recycling centers are near their scrap, then they can have fast turnaround for it. They can take chances because it's material that they've already paid for, and they can start applying additive manufacturing on the alloys that they want, that they're used to, that they perform for their applications. And obviously, if you can utilize recycled materials, you can have a large disruption in the cost, and that's also something that we're really trying to demonstrate and show. I was at the Munich Technology Conference last week, and Hans Langer, he's the godfather, I guess, of the printing industry. I don't know if that's an appropriate term, but he said that the largest barrier right now, or the thing that's going to stagnate the industry, is the cost of materials. And it's evident if you look at the productivity of the powder. One of my co-founders, Andy, he said, Guggenheim, the printing press, didn't print quickly overnight. So it's going to take time for the printers to develop. But what's going to happen once the printers do develop in productivity, powder is going to become one of the largest costs in it. So if you look at the bar graph, the purple is basically the cost of the printer and the cost for you to operate the printer. And right now, that's the largest piece of it, right? Printers are expensive and the productivity is very small. But it's going to change. The printers are going to become more productive. They probably won't reduce in price, but they're going to become more productive per dollar basically spent. And when that starts occurring, the delta, or basically the cost of the printer, is going to start shrinking, and the consumption of powder is going to start increasing. And so in the future, we believe that the most important thing to solve is the cost of the powder. And this is kind of evident in our strategy, but then also evident when you just start looking at how fast or how productive the printers have to be to start changing this paradigm. Earlier today, Desktop Metals presented, and they said that they were printing at rates of 10,000 centimeters cubed per hour. So they're already 10 times faster than these numbers. So if they actually reach scale, this is already a problem immediately. Why us? We fundamentally believe that our technology is going to have the ability to be alloy agnostic and to be a single melting step. So we've demonstrated, I think, 30 different additive manufacturing alloys. Niobium, which is a superconducting alloy. Inconel 718, we did that from downhole drill collar scrap. Ti-64, which is the kind of the industry standard, the workhorse in the titanium industry. Ti-1023 and Ti-553, which are landing gear specific alloys. RHA, which is rolled homogeneous armor. It's a high strength steel alloy. Copper and stainless steel, amongst others. But these are just the portfolio that we've been developing, materials that we've demonstrated that you can produce, and these were all produced from scrap materials. So our process, this is the reason why you should go to a single melting step. It's basically that right now the best way to produce metal powder is to first buy a wire, which seems like an odd idea because the wire didn't do anything for you to make the powder. And if you think about energy, time, and just cost, it costs a lot of money to make a wire to then just make powder. And fundamentally, we decided that you should just take molten material and you should turn that into metal powder. So that's where the biggest paradigm in this industry is going to occur, is when you cannot be dependent on the cost of wire as your watermark for powder cost, and instead you can start depending on the raw material cost, which would be scrap or virgin materials like master alloys, and then you can actually start having metal powders at similar cost of ingot, and that's going to open the door wide open for the use of additive manufacturing. Energy cost, this is pretty obvious if you think about all the steps that are required to basically produce a wire. AP&C is the first one that I show, that definitely the industry standard for metal powder, but extremely energy intensive. And a majority of that energy is actually consumed in producing the wire, which is really no effect in the powder. They're just using it because it's really hard to atomize metal powder consistently. I mean, it took us 3 years, and we really understood why they used wire, but fundamentally still believe that not using wire is a better way to do this. Then you have IGA, which is Electrode Induction Gas Atomization, and this process requires a small diameter ingot, like 2-inch diameter, and then you basically put an induction coil around it, and you drip melt it into an atomization die. And the process is really energy intensive because it takes a lot of energy to make that ingot, but it also takes a lot of energy to get that ingot hot enough, but then dripping into a point where you can do the atomization. It's also rather inefficient gas-wise, so gas consumption of an IGA is very high. And our process is a single melting step. It produces the metal powder either from virgin materials, which is the first of the two, or it can produce it from recycled materials, which would be the second, so the lower cost. Because you're basically using material that the energy has already been inputted to it, because it's metal. Then you need to look at, yeah, that's great. You can now get powder for lower cost, but is this really going to disrupt the industry? Is it going to be cost competitive to traditional means of manufacturing? And today, yes, especially in aerospace. So if you need to produce an aerospace component, this specific component is a landing gear component that we studied with a program that we have with the United States Air Force. And the part basically had a really high buy to fly. 15 to 1 and 17 to 1. So 17 pounds of titanium metal is required to produce 1 pound of flying titanium part. And once you start taking that into consideration, you didn't get that 17 pounds of metal for free, not for cost, not for energy. But instead, if you can use an additive manufacturing process, like either wire DD or DMLS, you can greatly reduce that buy to fly. And if you can apply recycling to that, you can get to where the MolyWorks line is, where it's the lowest energy consumption to basically produce an aerospace grade part. So the competition, I think that almost all startups have a slide that basically shows them in a corner where no one else is. But I fundamentally believe that there's no one else in the industry that is trying to develop recycling and distribute it. So if there is a powder producer that's in here that believes that their logo shouldn't be where it is, I'm happy to adjust it in the place that they would prefer it. But basically, if you have a distributed network of systems where you can recycle, you can reduce inventory costs, tariffs, import duties, shipping costs, and basically lead time. And all of those dramatically improve your effectiveness or your ability to adopt additive manufacturing. So our business model is pretty simple today. We would like to kind of advance it more toward a circular economy, but today it's basically take low value material and turn it into really high value material. And we can do that as recycling as a service, or we could sell powder into traditional means, just selling powder directly to a printer OEM or selling powder to a user to basically start getting the adoption of our materials. So we've demonstrated basically the titanium scrap to titanium powder and selling titanium titanium powder as a product. And then we've also produced aerospace grade materials that are 3D printed. and there's quite a big multiplier in the value of the parts from the scrap. So that $1 a pound is a pretty standard value for scrap, and the $1,100 a pound is kind of a general term for a 3D printed part that's aerospace grade. And what I think is really interesting is, I mean, there's multiple companies that produce more than 1 million pounds of scrap every year. And if you have the ability to take 1 million pounds of their scrap and convert it into 1 million pounds of printed part, it's $1 billion opportunity. So the numbers are real and the opportunity is great. So we have a strategic investor, and we said we would like some of their scrap. That was a very naive thing to say without really understanding their scrap. And so what happened is 5 days later, I got a call from my CTO, and he said, are we an oil and gas company now? Are you ordering drill rod? There's a 20-foot long downhole drill collar in our parking lot. It's 3,000 pounds, and I have no idea how we're going to pick this thing up. So we got 2 of them. Those are, they're downhole drill collars. They're Inconel 718. Each of them are, 3,000-ish pounds. They have segments where there's like some hard surface, or some tungsten carbide, basically, some hard face. So what we had to do was basically cut that down a little bit and get it to just where the bulk metal is. And then we took that bulk metal and we melted it and we atomized it into fine metal powder. And a lot of people seem to believe that recycling doesn't have traceability, but that would have great traceability. You know exactly what material that was made. It's one bulk piece, which is the argument a lot of people make that it's not traceable. But I think that it's actually more traceable if you considered your entire process in one closed loop and it was circular. So actually you could improve the traceability by using this method. We basically took that drill collar, chopped it up a little bit, turned it into metal powder, and then we started doing tests on the metal powder to demonstrate that the powder has good flowability, good morphology, good sphericity, all the things that are basically necessary to prove that the metal powder can print. And once you've done that, then you get it certified by an outside lab because no one believes a startup. So we certified both the incoming material, or we had an outside lab certify the incoming material, and then also the material that we produce. And one thing that did occur is that there is a slight increase in oxygen and nitrogen that occurs when you're just recycling powder and most of scrap, and most of that's on surfaces that have a lot of machining. And this isn't a hard thing to solve. You can solve it basically by putting more virgin material in with the scrap, so it could be a mixture. Also, the National Science Foundation program that I showed on the second slide is actually for us to develop a reducing plasma, and so that would allow us to extract oxygen from the melt. So that would actually allow us to be doing 100% scrap recycling methods. So we are attacking that kind of in both fields, one with technology development and then the other one with basic process development. And then you print things that are kind of stupid things that are just going to sit on your desk. And this is good for kind of proof of concept. It gets the people in your company excited that we did it, but this really doesn't go that far in demonstrating that people are going to believe in recycling, that people are going to use recycling, and people would be committed to recycling rather than going through traditional means. So what you have to do next is you have to really push your strategic to implement this, to really go after it. So we went to their tier 1 supplier. This is a tier 1 oil and gas supplier that basically first was a machine shop, basically doing a lot of machining for oil and gas parts, but then moved really heavily into additive manufacturing. I think they have 12 3D printers now. And we had the powder that was made from that downhole drill collar, and we put that into their machine, and they started printing density cubes, again, things that basically just sit on a desk that aren't that valuable, but are done by a contract manufacturer. And they basically proved, I mean, this letter says that it worked. I think he might have been a little bit surprised because there's an exclamation point on it, but it worked. It performed as well as the powder that he's traditionally using, and there's the density cubes. But that's still not enough, right? No one's going to believe that this is a viable option if you're just printing things that sit on a desk or density cubes, because almost everyone can print density cubes. And so we pushed a little harder, and then we got to a downhole flow diverter. So those are large. There's 120 kilograms of printed part there, so each of them are roughly 30 kilograms. They're real downhole parts. They're actually going to go downhole now. These just got finished 2 weeks ago. So the first picture that you see on the left is what it looked like as printed. So 4 of the components are printed. Also, you have test specimens that are on that build plate, tensile bars, fatigue specimens. And then you have the part that actually, after it's been printed, is the middle picture, and then it's been finished. So it has a final machining step, but significantly less post-processing or processing than it would if you took an ingot and tried to produce that part. And this part has kind of infinite opportunity to improve. So anything that has flow going through it that's a great application for additive manufacturing. And when you're not restricted by the capabilities of the machining, you can start actually applying the value of additive manufacturing to improve your application. So we're pretty excited about this opportunity, and we're really excited to have the opportunity to basically persuade a person that recycled material, if it's done right, has the potential to be a better product, has the potential to be a lower cost product, and a less environmentally impacting product. So this is still early days, but it's just a commitment to show that this isn't just a science experiment. This isn't producing just widgets that are going to sit on a desk. We're going after real applications. So this is the value chain again. This is another part that we actually produce. So there's that scrap, the downhole scrap, the metal powder that was produced, and then there's a turbine. So that's a fan intake turbine. And then we've also been doing the QR codes too for the traceability. So this is my favorite material. It's titanium, and surprisingly, titanium scrap is everywhere. You wouldn't think that the barrels up top is titanium scrap, but it is. And that material is really traceable. It's fully, it's dense, it's metal. And so it has a lot of value, but it's not being given any value if you sell it as scrap, $1 a pound. And then there's also printed parts that are scrap. I know additive manufacturing, it's supposed to be, you put it in, you click print, and out comes a great part, but that's not so much the truth all the time, especially in the prototyping phase. And just in the bottom left is 2 fill builds that we have, and I think a lot of you in here have more fill build. And so we were able to take traditional scrap, additive manufacturing scrap, and then on the far left corner, I guess it's right for you, that's actually forging scrap as well. So 3 different flavors of scrap. And there's our process, so you basically melt the materials, and then you atomize it, and then you have the fine metal particle, and then you print a landing gear component. So this component is a non-critical, non-structural component, but it has basically hydraulic fluid paths. And this is a piece of, or a part that basically has low supplier volume and it's limited by volume. And so if you need to start up this production, it's really costly. So additive manufacturing can be injected directly into the supply chain. Yes, it's going to be an upfront cost initially, where you're going to have to basically do the NRE to develop this build file. But then over the next 30 years, you can have the ability to basically click print and get this file on demand, or roughly on demand, instead of starting up a forging process or a casting process. In this case, we basically have 7 landing gear components. 3 of them are actually traditionally aluminum, forged aluminum, and we're going to replace all 7 of them with titanium. And most people would say, aerospace, you shouldn't do that because titanium's heavier. Well, we got really lucky. Apparently landing gear, depending on the part, you actually have to weight. So some of these were like front landing gear, and you actually had to add weight to it. So they were actually really happy with the concept that you could have titanium. But you could also just lattice the titanium. Titanium has like 700% better fatigue properties than aluminum. So in 30 years, you may replace the aluminum part 3-5 times. In 30 years, you may never replace the titanium part. Titanium part also has superior corrosion resistance. So almost all aluminum parts are going to have some type of paint on them, significant paint. And in titanium cases, you're going to have kind of a top coat paint, but that's really the only additional barrier that you're going to need. So So the metal powder market, I believe, is finally coming to maturity. The printing market also is becoming real. So when I started this endeavor, I think it was about 2014, 2015, and the venture capitalists would say, how big is your market? And I would say, it's less than 100 million. And then they would say, they like tap you on the head, it's like, they're there, yeah, come to me when the market's worth $1 billion. And we had the foresight to basically say that's not an acceptable answer. The market is going to grow, and now all that foresight and basically that trust in what additive could become is now coming to fruition. So the additive market, the printer sales grew 80% in 2018, and powder sales has grown 40% for the last 5 years. And it typically lags. So in years where you had large printer increases, that year the powder didn't increase very much, but the following year it had similar growth as what the printer sales was. So we expect 2019 to be a record year in powder sales, and we believe that if there is an ability to use and to adopt additive manufacturing, people are going to do it in a big way. And powder is going to be the thing that people need. So we hope to be that solution provider for them. So there's Matt and myself. That's the guy that basically builds melting furnaces on his front lawn and has a wife that is okay with doing that. And the concept that we're going after is a distributed recycling network, and our first place is in Cloverdale in California. We are actually trying our hardest to get a recycling center into Singapore by about this time next year as the first globalization or the first international footprint of the technology. So mostly thank you for the time and to listen to the conversation. And I hope in 2 weeks, if you have the opportunity to do Slingshot, you can be here and support basically bringing metal recycling to the Lion City. And if we need to, we can call it the Green Lion process. It'll be our version of the Green Lion, not turning base metals into gold, but turning your scrap into the printed parts of the future. So thank you very much for the opportunity to speak here today.